All right, this lecture is entitled Fender Stratocaster, and what it's going to do is it's going to introduce us to the wave equations. There's a lot of equations that are associated with waves, some of which are familiar and some of which are not. So the first thing we want to look at is says famous people feel they must perpetually be on the crest of a wave, not realizing that it is against all the rules of life. You can't be on top all the time. It isn't natural. And you should know that now because the crest of a wave automatically goes down to the trough of a wave. So let's look at the learning goals, and they are that you should understand the inverse relationship between period and frequency. We discussed that conceptually in the last one. You should understand what determines a wave velocity and manipulate the terms of this equation for velocity on a string. You should be able to use the wave equation to show the relationship between velocity, frequency, and wavelength. So a lot of math, a lot of equations in here. So the first thing we want to know is that you should already know this. This is the very first formula we talked about. It says the average velocity is equal to the displacement divided by the time. So when you take a look here, we're familiar with all these variables. There's nothing new there. So you should be able to apply it to the situation that we had in the lab. So in the lab, we generated a pulse wave that travels along a 2-meter string. So it traveled this way. It says the pulse travels down the spring and reflects back. So it actually came back on the other side. And it says to its original position in 1.5 seconds, what is the velocity of the wave on the string? So in this particular case, we are trying to figure out how fast the wave is moving along the string. Um, just to kind of clear things up, technically would look at it and say that the velocity is zero because it's actually in the same place that it started. You don't tend to do those sorts of things whenever we talk about sound and waves. It's not like walking forward and then coming back and saying you have a velocity of zero. So what we're referring to whenever we say this delta D term, I know the delta D is the displacement, but you're pretending like the wave did not reflect back. Okay, so the total length that it travels. And if you were to look, it's a 2-meter spring and it actually travels there and back, so it's a total of 4 meters that it travels. It's just because of the experiment itself that it actually reflected back. So the pulse travels down the spring and reflects back to its original position in 1.5 seconds. So you would say the time is 1.5 seconds. You would use the equation V equals delta D over delta T. And you would say, okay, 4 divided by 1.5, and that gives you a value of 2.67 seconds. Oh, excuse me, meters per second. And yes, I know that the velocity should technically be zero, but just realize that you have to read the question and kind of figure out what's going on here. But you're trying to figure out how fast the wave is on the string. It's just because of the experiment that it appears to be zero, but the wave is traveling 2.6 meters, 2.67 meters per second the entire time. So you should be able to do that. That's kind of a review stuff. You should have learned in the lab that increasing the frequency, the velocity didn't change. So whenever you increased how fast this thing was moving, there was no effect on the velocity of the wave. Increasing the frequency actually decreased the wavelength, and increasing the tension in the string, not the spring, actually increased the velocity as well. So there's a couple of things that you kind of figured out conceptually in the lab, and let's kind of explore those a little bit more. So the first thing is frequency. We talked about frequency being the inverse of period, but there's actually a mathematical relationship for it. It says frequency equals 1 over t. Frequency is actually measured in hertz. Okay, that's the unit. You see it a lot whenever you see like your radio station or how fast your computer processor is. It's usually measured in hertz or megahertz or gigahertz, those sorts of things. It's just the number of cycles that it complete per second. The next thing you take a look at is the period. Period is the time that it takes to complete one cycle, and that's measured with a stopwatch. So you should be able to do example B1. Example B1 says your favorite radio station is 820 kilohertz. Determine the period of this wave. So you would look at it and say, okay, well, the frequency is 820 kilohertz. So kilohertz is not what it's supposed to be in. I know the kilo of anything would be times 1,000. So I know that this is actually going to be 820,000 hertz. It's just like converting from kilometers to meters. I also know that I'm trying to solve for the period of the wave, and I know that the formula for that is frequency equals 1 over the period, or the same thing is period equals 1 over the frequency. So as a result of that, you end up getting 1 over 820,000 hertz. So the answer that you get whenever you plug everything in is you end up getting something like the period being 1.22 times 10 to the minus sixth seconds. The next example says, what is the frequency of a wave that completes 5 cycles in 15 seconds? So let's look at the definition of frequency. The definition of frequency is the number of cycles per second. So, in order to figure this out, I would actually take cycles and put it on top and say 5, and then number of seconds on the bottom, and that would be 15. So the answer would be 1/3 or 0.33 hertz. If I was trying to find the period of the wave, or how long it would take to do one wave, I would do seconds divided by number of cycles, which in this case would be 15 divided by 5, or 3 seconds. And if you look, these two things are inverses of one another, just like we said they would be in the formula. So just recognize the fact that as frequency goes up, period goes down, and they're inverses of one another. So whatever, if one's 10, the other one's 1 over 10. So next we have the velocity equation, and this is the equation that is most commonly used whenever we talk about waves. You're going to use this one over and over and over again, so you need to be very familiar with it. The first thing that you have is velocity. Velocity, we've already talked about, it's how fast something's moving. It's the rate of change in position. It's measured in meters per second. There's nothing new that's there. The next thing is, this is the Greek letter lambda, and the Greek letter lambda stands for the wavelength. Now remember, when we talked about this earlier conceptually, we said that wavelength is the distance between identical parts of a wave. And we said you could measure the wavelength here, or you could measure the wavelength here, but it's got to be between identical parts of the same wave. And that's what you see here. This is the wavelength, and it is measured in meters. Now, a lot of times you will see the wavelength in centimeters and millimeters and nanometers when we talk about light, but it should be in meters whenever you do your calculations. And then finally we have the frequency, and the frequency is the number of cycles per second. It should be measured in the unit of hertz, but you tend to see it in things like kilohertz and megahertz, gigahertz, even terahertz when we talk about light. So you need to be familiar with the conversion between those two things. So this is the equation V equals lambda F, and it's kind of going to govern everything that you see here. So people say, well, how do the units match up if velocity is in meters per second and wavelength is in meters and frequency is in hertz? Those don't match up, and this equation shouldn't work. Well, it depends on what you look at in terms of your definition of hertz. Remember, the formula for frequency was 1 over the period, okay? And period was measured in seconds. So really, frequency is 1 over seconds. That's what a hertz is. Hertz is 1 over seconds. So now if you kind of cross this out and put 1 over seconds, you see that the units do in fact match up, and they go through, and you get meters per second. So since this is a math equation, a lot of times what you need to do is you need to just work with this particular equation. You need to see this equation in action. So the first one says, if this wave has a frequency of 200 FM, okay, we know we don't have 200 FM, it's like 107 FM, but if it's 200 FM, then what is the velocity of this particular wave? So the equation that we're going to be using is the equation V equals lambda F. This right here is going to be the frequency, and it even tells you that you're going to have to convert. So it says you have 200 FM, and that 1 FM is 1 megahertz. But that's still not where you need to be. Remember, you do need to be in hertz. So the conversion between mega anything and our standard unit would be 1 megahertz is 1 times 10 to the 6th hertz. And that would allow you to get this as 2.0 times 10 to the 8th hertz. Next, you see this graph right here. It says, what is the velocity of this wave? If you were to look, you have a trough, a trough, and a trough, and it gives you the reading of 3 meters. So 3 meters represents not one wave, but 2 waves. Now remember, the definition of wavelength is the length of one wave. So if you have 2 waves in 3 meters, you have to cut it in half, and you get a wavelength of 1.5 meters. So now I have a frequency and I have a wavelength. What I can now do is I can now go ahead and I can plug in and I can solve for the velocity. So this is my frequency and this is my wavelength. So I'd plug in, I would say, okay, 1.5 times 2.0 times 10 to the 8th, and you end up getting 3 times 10 to the 8th meters per second. Now, as when we talk about light a little bit later this year, you'll realize that the speed of light is actually 3 times 10 to the 8th. And actually, radio waves travel at the speed of light. But that's what we'll talk about a little bit later. For now, you should just be able to say V equals lambda F, and you should be able to get those terms. Next, this is determine the velocity of an ocean wave that has a frequency of 3 hertz and a wavelength of 5 meters. So we say, okay, I have a frequency of 3 hertz and I have a wavelength of 5 meters. The equation is V equals lambda F. It's in hertz and meters, so I don't have to convert anything. And so I would now say, okay, equals 5 times 3, which is 15 meters per second. Next, you have earthquakes. Earthquakes are actually a combination of both a transverse and a longitudinal wave. It consists of two different waves. The first one is the P wave, or the longitudinal wave, and it travels really, really fast. It travels about 8 kilometers per second, but it's not the cause of a lot of the damage. It travels through the earth, and since it doesn't make the earth move upwards, it doesn't really cause much damage. Now, the S wave, which is the transverse wave, travels at about 60% of the speed of the P wave. And the reason why we say 60% is the P wave doesn't always travel at 8. It depends on what it's traveling in, whether it's traveling in sand or gravel or dirt. So because of that, we can't say for certain how fast the S wave is. We can't actually say for certain how fast the P wave is until it's in a specific location. But on average, the S wave travels about 60% of the P wave, and it's the cause of the major damage. But because of this difference in velocity, it actually allows for the detection of earthquake waves. So you have an earthquake that occurs, and then you have like a building right here. Because the P wave gets there first, if you can detect the P wave, you have a few seconds to get ready for the S wave, which is going to cause the damage. And so that's kind of the basis behind earthquake alarms. You can start to kind of notify people so that they can protect themselves in case of an earthquake. In this one, it says you have the epicenter of an earthquake is 20 kilometers away. It says, how long do you have after the P wave arrives to prepare for the S wave, assuming the P wave travels at 5 kilometers per second? So, what we have here is we say, I have an earthquake that occurs right here, and then I'm over here 20 kilometers away. Now, both waves have to travel the 20 kilometers. The first wave is the P wave, and it travels at 5 kilometers per second, or 5,000 meters per second. It has to travel a displacement of 20,000 meters. Okay. The second wave is going to have a velocity 60% of that. So it's going to be 60% of the 5 kilometers per second, or 3,000 meters per second. And it is going to travel the same 20,000 meters. So next, what we see is we say, all right, now that you've got these things going on right here, you can figure out the time that's associated with each one of these. So you would say V equals delta D over T, and you would plug in your numbers. You would say, okay, 5,000 equals 20,000 divided by T, and you would solve for T. When you solve for the time in the first case, you end up getting about 4 seconds. Okay, 4 seconds is how long it takes to travel those 20 kilometers. If you were to do the same thing in the other case, where you'd have 20,000, you'd have 3,000 equals 20,000 over T, what you would see is you would see that it would take about 6.67 seconds. So the question says, how long do you have after the P wave arrives to prepare for the S wave? Well, if it takes 4 seconds for the P wave to arrive and 6.67 seconds for the S wave to arrive, what you can do is you can subtract those two and get your final answer, with your final answer being 2.67 seconds. That right there is how much warning time you have. And you say, well, that's not a whole lot of time. That's enough time for you to get under a desk or to get in a door frame or to get someplace that you can protect yourself from falling debris. So it's nice to be able to do that. So now let's take a look. Now we talk about the velocity of a wave. The velocity depends on the medium in which it travels. It does not depend on how much energy you put into the string. So for example, if you were to all of a sudden put a lot of energy into this particular wave, it would just make it move higher or lower. Okay, it would not make it move faster or slower. Okay, so the energy that you put in a wave actually has nothing to do with how fast it will travel. Instead, it depends solely on the medium in which it travels. So if you were to put it in water, it would travel a certain speed. If you were to put it in air, it would travel a certain speed. If you were to put it in steel or a string, it would travel a certain speed. So the only way that you can really affect the velocity of a wave is to affect the medium in which it travels. So if you were to look at it in terms of a guitar, the mass of a string, the thicker or thinner, you can affect the velocity of a wave, and the pull in the string, you can actually affect it as well. And this is actually directly analogous to the lab that we did, where we changed the string, or we didn't change the string, but we changed how tight we pulled the string. Whenever you tune a guitar, you're actually increasing the tension in the string or decreasing the tension in the string to either make it go higher or lower because you're changing the velocity. So we actually can take that and turn it into an equation where the mass of the string and the pull on the string will tell us kind of what the velocity is, and you can extend that out to see what the velocity, or excuse me, what the frequency would be. So you would see that the thicker the string is, kind of the lower the sound you get. So if we take a look at the equation, and this actually didn't come out real well, but it says the velocity of a wave on a string is equal to the square root of the tension divided by this mu term. Okay, so the tension we've talked about before is how much you pull the string. It's measured with the Newton spring scale. You guys did that in the lab. This mu term is actually called the linear density. The linear density represents the mass of the string divided by the length of the string. It's the linear density. It's a mass to length ratio. Okay, and then finally you have the velocity, and the velocity we've already talked about is what's affected by these things. So the more you increase the tension, the more you increase the velocity, but it's not a one-to-one rate. Okay, if you were to increase the tension by a factor of 4, that would double the velocity because of this square root term. Okay, if you were to increase the mass of the string to make the string thicker, okay, what you would do is you would actually decrease the velocity. Okay, so you need to look at these relationships, and it's the same thing. You would have to increase this by a factor of 4 to decrease this by a factor of 2. So you need to be familiar with this equation and kind of how to use it. Now this is an extension. It is a little bit beyond what we would expect you to know right away. You should be able to get to these if you're looking at kind of an A-level question. So now we have a guitar wants to play a middle C, and you're given the equation, or the frequency is 523.251. It says the guitar is constructed with a 1 meter piece of string with a mass of 0.005. What tension must the string have to produce the note indicated? So this requires a lot of information for us to know. The first thing is that we know that it is a 1 meter string. The second thing is that we know the frequency that's right there. So if you remember the lab that we talked about in terms of harmonics, remember that one harmonic, which is what you have here, equals half of a wavelength. So the wavelength would actually be 2 meters. And once you have the wavelength as 2 meters, and then you have the frequency is 523.251 hertz, that actually gives you enough information to calculate the velocity using v equals lambda f. So you can go ahead and do that. And when you plug those numbers in, you get a velocity of 1046.502, which is pretty fast. So now we take a look at this and we say, okay, well, how can I produce this on this particular guitar? And I would say, okay, velocity is equal to the square root of the tension divided by the linear density, and it tells me that I have the length of the string is 1 meter, and that the mass is 0.005. So that actually tells me that my linear density would be 0.005, because 0.005 divided by 1 is 0.005. Okay, so now I have 1046.502 equals the square root of Ft divided by 0.005. So that actually gives me all the information that I need to be able to solve for the tension. Now, one of the things that you need to be careful about is how you actually solve this mathematically. Okay, the first thing that you should do is you should square both sides. When you square both sides, it allows you to get rid of this square root sign. Once you do that, then you can multiply it by 0.005. And you would do the same thing over here by 0.005. So in other words, you would have 1046 squared times 0.005. 0.005 is not included in the square though. When you do this, you should get a final answer of about 5,480 newtons. And in the second example, it says, what is the mass what is the mass of a 0.8 meter wire that generates a wave of 35 meters per second when subjected to 150 newtons of force? So we're going to use the same equation. Velocity is equal to the square root of Ft divided by mu, where I have the length of the wire, which is 0.8. I have the velocity, which is 35. I have the force, which is 150. And then I can go ahead and plug in and solve. I would say 35 equals the square root of 150 divided by mu. So I would square both sides. And when you square both sides, you end up getting 35 squared equals 150 divided by mu. And you can go ahead and solve, and you can say, well, mu then is going to be 150 divided by 35 squared. But then don't forget that mu is really mass divided by length. So you would actually have to multiply both sides by the length, which is 0.8. And when you do that, that allows you to get the mass of the string, which you should be able to figure out is 10.2 kilograms. So there is a lot of math going on in this particular equation or this particular lecture. You need to be able to be familiar with the formulas. If you're focusing on them, you need to be able to do V equals lambda F first and foremost, and then the inverse relationship between frequency and period, and then review V equals D over T. Okay, and then this one is last, but you do need to do V equals lambda F is the most important of all of those.